In this video, we're going to talk about images that are formed from a single surface. I'm going to go over two cases. We're going to talk about the flat surface, and what about a spherical surface? There are lots of other types of surfaces you could talk about, but we'll just look at those two cases. So the flat surface you can think about as being like looking at something underwater. For example, this fish underneath a stream. Now, what we want to talk about is where do you actually see the fish? Now, in this picture, you obviously know where you see the fish. So the question is, where actually is the fish? And you might say, well, it's just right in front of you. You can see it. But here's the problem. You can think about this picture sort of from a third point of view perspective. And the light ray that goes from the fish, which I've denoted by a star, a solid black star, travels to your eye not in a straight line because it has to go through the interface between the water and the air. And as it crosses that boundary, it'll bend away from the normal as it goes from a slow to a fast medium. What that means is that your brain, which assumes that the fish is right here where you see it, directly in line with where you're looking at, would see the fish somewhere above where it actually is. So while I may see the fish right here, the fish itself may be a little bit below there, depending on how deep it is and the angle that I'm looking at. But it's always a little bit below. So let's talk about that. And this star here, by the way, if it wasn't clear, was where I would see the fish. That's actually there. It's that light gray star. So how much deeper is the fish in the water than what I actually see it as? You can use these equations, which are similar to the thin lens equation, in order to figure that out. Now, it depends on a couple of things. It depends on the index of refraction of these two materials. So N1 and N2, as I'm calling them. N1 is the index of refraction of where the object is in, so the actual place like in the water that I'm looking at it. And N2 is the index of refraction of the other other medium, the one that I'm looking from. And I'll use O to mean the distance, or the depth in this case, of the fish, where the object is actually creating the light. And I is the image distance, so that's the distance from that surface down to it. Now here we don't have a lens, but we can sort of generalize their notation with I and O. Where before was the distance to the lens, the purpose of the lens was to bend the light. Here what bends the light is just a single surface, so we'll measure our distances from that location. And the magnification equation looks similar to before, and again what we'll have is the notation that a positive I would mean that it is you actually see the water out here in the air, so you're going to end up getting a negative I most of this time. And the right side up, upside down still holds. And note here that if you had N1 equals to N2, which would be this sort of the case where you had no refraction because you have the same type of material or medium above and below, or at least they share the same speed of light inside of them, which is the only property that matters in this case. Then what you'd find is that since these two things are equal to each other, O would just equal to negative I, which means physically that the image location would be on top of the object because they just have the opposite signs convention. Whether one's, this is a negative value for I and then a positive value for O, for example. And what you'd find here is that the magnification is equal to positive 1. Because I and O have opposite signs, that would cancel against this, but they have the equal magnitudes. N1 and N2 would be the same, so that would just cancel out as well, and you just have magnification of 1, meaning it is not inverted and it's the same size. But if they are not the same index of refraction, you'll find that it appears either larger or smaller, depending on the relative sizes of the indices of refraction. Normally N1 is larger, because you look, say, from air looking into water. We don't typically look from water into air. So in that case, you tend to find the denominator is, so the numerator is larger, so it actually looks slightly larger than the actual size of the object. And if you ever say thrown a penny into water, you'll sometimes notice that it looks larger than normal. Now the other case we will talk about is if you have a spherical surface. So here this is like looking into a crystal ball, or say looking into a fishbowl. And you have some object inside, like a fish in a fishbowl, and it's emitting light. the light will come out through the surface. The light that goes directly outwards and hits perpendicular to the surface will come straight through. But the light that's slightly offset will be bent away from the normal. And if you trace back in a straight line, what you'll find is it looks like the fish is again a little bit closer to the surface. So we want to use these same sort of equations as before. Here we have a slight difference, and now that we have a curvature to the actual bowl, which is going to have an additional effect. And that's R here is the radius of the bowl. Note that if the radius was really large, like for example, it was the ocean, which is roughly a sphere, but if you are sitting on a placid on the ocean while there's no wind and it's just very flat, it'll look like it's completely flat. So it'll look like this case right here. So you should find the same formula for the image location if R is large enough. And here, if R becomes very large, the right-hand side becomes 0, and the equation is now the same. The magnification isn't changed at all. We just now have this additional term that relates to the curvature of this ball. And again, what you have is that if n1 equals n2, so that the light rays don't bend at all, then you find that the object and the image appear at the same location, which means that they have opposite signs, because again, they physically mean an image is positive if it's in the air, in this case, and it would be negative in the water. And that would mean that the numerators are the same, and then the right-hand side is 0 because these two values equal each other.